Hello and a very warm welcome to our little series of online seminars this season. My name is Alfred Huber and I will guide you through the seminars today. I'm not alone today, so I want to introduce before we start to go into topics, I want to introduce my co-pilot or my navigator on this flight today before I forget it. Alex, you want to introduce yourself?
Yes, hello and a warm welcome from my side. My name is Alexander Boy and I'm product manager here for our product series. We want to give you some instructions for our webinar today. You have a control panel on your screen, on your desk, maybe on the left or on the right. There is a chat part where you can send us some questions. So feel free when you have any questions to some points in the webinar and contact me and I will answer this to you. We have also a hands-out series where is attachments on it where you can download when the webinar is running. It's specially for you. Have a good time and I give to our presenter, Alfred. See you later.
Thank you very much, Alex, for your quick introduction to the control panel, which is somewhere sitting at your screen. And yes, feel free to answer questions during the whole presentation. So not shifted to the end of the presentation. So Alex is sitting in front of me and is controlling the questions and giving answers. And after the presentation, we will discuss the major questions. If you can't discuss questions right now, we'll definitely answer it on the later stage. So as I mentioned, we are having a little series of online seminars in the next 2 weeks. So this week we are going to start with very basic fundamentals of networks. Next week we're going a little deeper into these, especially into testing, which is our domain. So today we're starting with copper fundamentals, some really basics of the copper networks and the testing of the copper networks. So what's the agenda for the next hour? First of all, we want to politely introduce, of course, ourselves. Who is Softing? Who is the company? Then we're talking about where these networks should go into. We're talking about structured cabling, especially on the example of an office situation. Then we dig deeper into the topic and talking about performance levels of networks. And finally, we have to verify and test the performance levels of the networks. And this is where our instruments jump in. So let's start with the company first. Who is Softing? Softing is a mid-sized German company. The headquarters where we are currently is in Hahn near Munich. If you look from the distance, it's at Munich, in Munich. The company was founded in 1979, went public in 2000. Approximately turnover was last year 85 million euros. Approximately 400 people are employed here. And we also have people spread around the whole globe, let's say. As you can see, we have owned local people in various areas of this world. Softing itself sits on 3 columns. The 3 columns are automotive, IT networks, and industrial, which is actually industrial automation. So what are doing the colleagues? Automotive, they are developing test equipment for controls in a car, and so they are very deep in that testing of cars, performance of cars. Industrial automation, they are helping people to set up production lines. The most problem production has is often that every different machinery in a production line is speaking a different language, a different protocol, and to connect different languages, they need proper gateways. It's a proper definition of the name, and the colleagues of industrial automation are providing these kind of gateways to allow a continuous flow of information in a production line. We from IT networks, we're sitting a little bit in the middle of these columns. So our job is to provide test equipment for networks, especially Ethernet-based networks. We're coming from the structured office buildings, cablings. That's where we are coming from. The interesting thing is that these networks we are used to find in offices, the Ethernet networks are also moving and spreading out now into other areas, especially industrial area. There is the old slogan, Ethernet goes industry, which is more and more the fact. So I think it was in 2017 was the turning point that more Ethernet-based industrial product lines were set up as any other combination of field bus system before. Automotive, all of us know cars are getting more intelligent, trucks getting intelligence. We have autonomous driving, and to control all the cameras, the sensors, and to provide the proper steering and braking, you need also network in a car, and these networks are based on Ethernet again. So everywhere where Ethernet is moving in, you need the same more or less test equipment, and this is why we are sitting so prominent here in between the columns of automotive and industrial, because this is Ethernet for the future, let's say. Okay, that's our job, to provide test and measurement equipment for the Ethernet networks. Located, I told you earlier, we are spread around the whole world. Just to see the map here again. So Munich is the headquarter. We have a very strong company in Knoxville in America, serving the Americas. We have a R&D department in Singapore and also serving the Pacific Asia market. We have sales office, pure sales office sits around in France, in Spain, and Vienna. In Italy, we got one, and of course, China, in Shanghai, we got sales offices. This is to cover and to spread out the products over the world. Okay, let's have a quick view to the instruments we are providing. So the bottom line is the network sniffer, the wave expert. This is a very dedicated instrument to a very special application to analyze traffic over the air. So I call it always a very intelligent antenna, which is providing a lot of data for later analysis to programs like Wiresharks. So that's a little bit of a niche product for us. So our real products are starting at the verifier level. Verifiers, very basic test equipment. We see later on what the job of a verifier is, and you see a few of these red buttons on it, new. So there we currently are replacing an existing product line more or less completely with new products. On top, more intelligent products are qualifiers. Qualifiers are not just verifying cabling, they are also testing cabling. And to see what performance level we can get out of a cabling, it's a way to document the quality, the transmission quality of a network system. On top of this are sitting the certifiers, we will see later on, and certifiers is RF measurements or OTDR measurements. By the way, tomorrow we're going to talk about fiber optics. Today is the copper part only. And this is how we distinguish between the different levels of our test and measurement equipment. Okay, let's move on in the agenda. So let's talk about the structured balanced twisted pair cabling, the classical three-level model of office cabling, and what components are used in those structures. So here is our challenge. So we have a company, has 3 buildings spread over a certain campus area. How to connect these 2 or 3 buildings to properly communicate, to allow communication between all the buildings. So the first level we start is called primary level. The primary level, the campus level, is usually done with fiber optics. So there's single mode is the expression they use here. Single mode cabling is doing the connections between the different buildings. So now we have the buildings connected. Now what we want to connect are the different floors in the building. To connect the different floors in the building, there's secondary cabling, which is also done in multi-mode fiber typically. We will see tomorrow what the difference is between multi-mode and single mode. And when we come to the floor itself, interestingly, we are changing usually the media. We are going now to copper. There are various reasons for that, and it has to do with PoE, it has to do with costs for active components, and so on. Okay, and this is the third level, the horizontal cabling, the floor cabling called. There are various names out there. And another one, a little interesting one, is nowadays no network without Wi-Fi. So we also got Wi-Fi in a building, so needs also certain kind of testing. So let's start with the floor cabling. The floor cabling made out of copper, and the first thing that goes into the wall is the cable itself. When we look to the cable, there are a few different ways to construct the cable. These are the most popular ways to use a cable. The cable we're using nowadays is called a twisted pair cable. So you can see from the picture, we have pairs of data, pairs of wires which transport the data in a balanced system. These wires are color coded, so we got standardized colors in that cable. Where is the main difference between the different sorts of cable? One type of cable is called the UTP cables. UTP cables, unshielded twisted pair cables. As the name says, it's just the wire itself with some insulation around it with certain colors, and everything is together in one outer sheet. That's cabling which is most used on the world, honestly. So has some limitation if it comes up to higher frequencies. There are words interesting like aliens, alien crosstalk, and so on. More professional cable, let's say, is called STP, shielded twisted pair cable. That cable is used 95% minimum here in Germany, for example. It also has 4 pairs of twisted cable or twisted wires. Each pair is surrounded with some shield foil, and around the four pairs with the foil is how to say, it's some outer materials, some metal around it. In different ways can it be constructed. Usually you see these bright outside there. Okay, there's the two main sorts of cable which are used in our world. The good thing is on this cable is that the colors are standardized we use in this cable. That helps us for the next step to connect it to some connectors. Here a quick look to the other sorts of cable. This is a page out of a standard and how the name is derived. So what you see here is on the top line, you'll see the two cables we saw before in a different graphic. The cable with the shield around it, around the pairs and around the complete pairs, is called S/FTP. And if you read the word backwards, you read it like TP. It's a twisted pair. Around the twisted pair is a foil. Around the whole system of the 4 twisted pairs is the braid shield around it. Okay. On the other side is the U/UTP cable. That's the completely unshielded cable without any metal support in this, any foil or any braid on this. And there are also a few kinds of variances of this. When it comes to testing, the tester is only interested, is there a 9th connection between the two ends? It does not take into account how this 9th connection is done. Is it the braid shield, is it the foil sheet, whatever it is. So that's already looking into field testing. So these are the kind of cable we can use. So let's look to some properties of the cables. So let's show a few parameters of the cables. The performance of these cables is in ranges expressed in categories. The typically used one is category 5 to category 8.2 nowadays. As you can see in this little table, we have fixed bandwidth steps in which we are working, so 1 to 100 megahertz, 1 to 250, 1 to 500, and so on. And in the various standards worlds, we have the 2 standards world, the ANSI TIRE, which is typically the American standard world. We have category 5E, which stands for 100 megahertz bandwidth of the cable, or Cat6, which stands for 250 megahertz. We have no definition, no standard in America for cables going up to 600 megahertz or to 1000 megahertz. But we have, again, specification in the American standards going up to Cat8 to 2000 megahertz, which we need to transport 40 gigabit Ethernet. In the ISO, in the international standard, or the European standard derives from this international standard, we have also these categories, but a little bit different in naming. So we have category 5, no E on this. So we just see from the issue date what category 5 we want. Then we have category 6 and category 6A. And as you can see on category 6A, we have the A a little bit set lower. And this has some meaning because it has a meaning in the component. There's a different specification behind the international definition of Cat6A and the American definition of Cat6A. We also have Cat7 and Cat7A. So there are in-between standards, and we also end up at 2000 megahertz. But in 2000 megahertz, we also distinguish between category 8.1, which is actually a system which is based on RJ45, and we have a Cat 8.2, also going up to 2000 megahertz, but this is a system based on different connectors we see later on. Okay, colors, the colors of the cable. So the wire colors, as I said earlier, is specified. which helps us definitely in connecting this to the proper ports. The chase colors are not standardized, allows no conclusion about the performance level. This is something people are confusing, because you have cable in yellow, in orange, in blue, and some people try to put performance levels to the colors. So the outside color has no relation to the performance of the cable. It might be some performance steps within one manufacturer, but we also have manufacturers where all the data cable in all categories have the same color. So the outside color is not an orientation for performance level. Diameters of the conductors inside. Now we are digging into the cable itself. The conductor itself, the diameter is expressed in AWG, American wire gauge. And we have two diameters which we use usually on data cables if the target is to build a network link up to 90 meters, a typical length, 90 meters plus 2 times 5 meters to go up to 100 meters for a transmission channel. Okay, these conductor diameters to make it up to 90 meters are AWG 22 and 23. So the thicker the cable is, the better the performance is for insertion loss and for resistance. But if the cable gets too thick, it doesn't fit into the connectors anymore. This is why typically there's a limitation how thick one of these wires might be. And there's also a limitation how thin it could be, because it's getting too thin. We can't make the 90 meters anymore. So every AWG, typically larger than 23, is either some fixed wires for nowadays called special home cables, which don't make the 90 meters, just go up to 60 meters, but are smaller in diameter. The whole cable is smaller and can be easily installed into a single house and can make the turns easier and so on. But it stops usually at 60 meters. Or it's a cable with stranded conductors, which is typically used in patch cords. So if you use patch cord material with stranded cables and try to do a 90 meter link, that would not work at all. So number of wire pairs. Currently, we are working with cables which are containing 4 pairs of wires. That's currently the standard universal cabling for gigabit Ethernet application, 1 gigabit as we use currently, 10 gigabit as certain people already have started to use. So we need 4 pairs of wire. When we started with Ethernet in the older days, we started with 2 wire pairs transporting the data, but this is limited to Ethernet up to 100 megabits. After 100 megabits going up to 1 gigabit, the way of sending the signals has changed completely, and we needed 4 pairs for transmitting. But these 100 megabits are still very common, not in the office environment anymore, but in industrial environment. A very prominent representative for this is Profinet, which is using up to, or which is working up to 100 megabit Ethernet, and 2 pairs are completely enough. Now there's a new tendency even to reduce the number of wire pairs. It's called single pair Ethernet. That's a wave that's rolling through the world since 1.5 and 2 years. And so we are going to reduce the number of pairs really down to where we started once with our analog telephone, to 1 single pair. Honestly, the cable is a little bit more complex as the telephone cable was in the first days. We are talking here about bandwidth going up to 600 megahertz to 1200 megahertz on a single pair cabling. Where they start, I think, first to be really spread out is, again, the industrial environment. They are very, very far already with defining the applications for this. So this is a tendency which we'll see over the next years more and more, going back to single pair Ethernet to 1 pair transporting Ethernet. It has its limitations, and it's not there's a discussion, is it really a standardized universal structure cabling, or is it more related a cabling which is definitely referring to an individual Ethernet application. So, but we will see more on this. And yep, I think next year will be the big year for single pair Ethernet, also on the testing and measurement front. Okay, how does signal transmission work in a twisted pair? So we are using, to transport our signals, we are using balanced signals. So equal but opposite currents, that's good. So we don't create electromagnetic fields around our cables. Equal but opposite fields, all fields balance each other out. So the idea of using balanced signal is definitely to avoid any electromagnetic fields surrounding the pairs and surrounding the cable. So to keep it very safe against external influence and not to work as an antenna to influence outside world. Shorter distance from conductors reduces impedance and external interference influences. So the better the mechanical structure of a cable is, the better the RF performance is. And let's have a look to the way how we transmit signals now on a twisted pair cable. As you can see on the right side, this is the way of the electromagnetic fields crossing out each other's on a properly balanced system. Balanced system means on the one side you got a transmitter. This transmitter tries to shift now these information we get here, ships now to the other side, transmits to the other side. How is it done? As you can see here, we take the signal and put it onto this wire here via a simple amplifier, and it's the same signal as is coming out from the transmitter. On the other line, we have an inverter, and this inverter is just inverting the amplitude. So we have now in parallel traveling to the other side the positive and the negative signal, and this is traveling to here. On the end of this transmission line, we see a differential amplifier. So if we take the difference between the negative signal and the positive signal, we are back to our transmitted signal on the receiver side. So what the advantage of this way of transmitting the signal is, if there comes something from the outside, it's called Störung. I left the German word in this. So this Störung is now induced into both lines the same way. And this will end up in our signals. And if it ends up on our signals, the signals will look like this one here. So we get on this one, we get here our spike built into the waveform, and here it's on top of the waveform. So it went in both signals, but in both signals it's the same amplitude, it's the same direction of the amplitude. And now if it runs this signal through the differential amplifier, this one will eliminate itself. And at the end, we still receive the signal we transmitted from the beginning. So that's the big advantage of this balanced transmission of signals. Okay, so that's the way it works. We saw the cable. How to get the cable to our system? We need connectors. And the most prominent and dominant connector we're using is the RJ45, the standard connector for categories 3 up to 8.1, so from 16 megahertz going up to 2000 megahertz, and is described in a standard series called IAC 60603-7-X's. Okay, how does it look like? That's the modern way of RJ45. You see these cable checks we have here, and they are mounted into these holders. And on the panel side, you see these panels where you just click these modules in. That's a common up-to-date way to set up a link, to build a link. A little bit back in the history, we had this kind with some IDC components in there, where you just have to lay out properly the cable, then you use these little machines to get it into the contacts. Okay, this is the check side, let's say. This is where the plug goes in. This is the way the plug looks. I think everybody has already seen this. We don't have to do much explanation on the RJ45. The interesting thing on the RJ45 is now there are RJ45 plugs out in the field which directly connect to a cable, to a installation cable. So not a patch cord only, but to an installation cable, because there are new systems now where we combine on the one side a jack, on the other side we directly have a plug. But we will talk about these things next week in the advanced courses. Something which is very important to know on the RJ45 is colors. Color coding. Nobody likes it, but we still get it. There are 2 existing color codes for an RJ45 existing. And unfortunately, it's in the standards since the beginning of the standards, and it has some history in the old telephone system. Doesn't make sense, because if you ask people, what's the technical difference between the 2 color codings we got? There is no technical difference nowadays anymore. So there is no advantage and no disadvantage, but it's still existing, and we still have to cope with that. And there's also another historical stuff in these color codings, and it's about where to nail down the pairs. Usually you got 4 pairs, 8 wires from the cable. You got 8 contacts in your RJ45. So if you think logic, you would just connect pair 1 with the pin 1, 2, 3, 4, 5, 6, 7, 8. That sounds logic, but it's not logic as it is in standards. The standards are historical ones. And the standards are starting with the first application for any cabling, which was analog telephony. The analog telephony also started with an RJ45 connector, not an RJ45, but an RJ connector, the Western connector with 4 pins. And what was used on the first time on the analog telephone, the inner pins of this 4-pin connector. So nowadays, when we start to build a link, we also start with the inner connectors, which is nowadays 4 or 5. After the analog telephone, there was ISDN. ISDN was digital telephony. What was available on the connector? The 2 outer pins of this 4-pin connector. So we went for the outer pins. Today, we're doing the same. So there's a pair now, which is 3 and 6. So in the middle, we have 4, 5, then we have 3, 6 surrounding it. Later on, this 4-pin connector was extended to an 8-pin connector, and 1 pair was added on top, and 1 pair was added at the end. And that's not very logical to do it this way. It's backwards compatible. So if you nowadays build a data center to the most modern standards, to category 8, to transmit 40 gigabits over copper, you still lay it out to be backwards compatible to an old analog telephone. That doesn't make too much sense. Unfortunately, it's still in the standards, and they recently started to change this. So it's still existing. It's driving us into problems when it comes to RF, to high frequency, because we are spreading out 1 pair around another one. That is crucial, and that is cruel, and it's generating crosstalk, which we don't want. And to make this thing really complex this is not only 1 color code which is allowed, but there are 2 color codes, 2 different color codes. The only pairs which are swapping the colors is the green-white one and the orange-white one. Okay. Reason, historical reason. Okay, so every installer has to be very careful to make sure that on 1 link, he's using the same color coding on both sides. Otherwise, we run into a fail. Okay, let's have a closer look to the RJ45, not to the RJ45, to other connectors, which also used in the networks. These connectors were once thought to be the future of connectors in a data network system. And we have 2 which are standardized, and standardized means going up to higher frequencies, higher bandwidth, and extremely better next performance. Remember the story with these 4 pairs, with its 2 pairs surrounding the other pair. That's solved in these kind of connectors to go up to higher next performance levels. And one is the GG45 from the company Nexans. This one has 8 connectors on the top row, and here we are, and 2 pairs of connectors in the lower row. So it has 12 connectors. And to make the trick to go to high performance, there is a special plug which has also a different setup of the connectors of the pins. So if this connector, the GG45 plug, is put into this jack, the nose you can see here is pressing a switch, an internal switch in the jack, and this switch internally is putting the middle 4, the problematic 3, 6, 4, 5 pairs to ground, and leads the signal to the new lower pairs in these lower corners. That's very complex, and it's a mechanical switch, but this gives us a very high next performance. But it's very expensive as well, or far higher expensive than RJ45. There's also an alternative connector in the standards. This one here is called the Terra from the company Simon, and Simon designed a how to say, a multimedia connector. This is not backwards compatible to RJ45. This one is. This is not. But you're allowed to use this connector as well in a standardized cabling installation if you want to go up to higher frequencies. And there are also non-standardized connectors which are very popular. This one here It's called MMC Pro. Older name was EC7 from a Swiss company, BKS. It's also a 4 chambers connector, as we call it. And this connector, it has fantastic RF performance. But it never made it into the standards. Maybe it was too good for the standards, but I think the Swiss company didn't want to share the patents. That's what the knockout feature for this connector. But you see this connector here around, especially Germany, Austria area. You see it sometimes on home buildings, single homes, or in certain applications where high bandwidth is required. This connector actually goes up to 2.6 gigahertz. So you can transmit satellite signal over this connector, over a more or less standard data cable with 8 wires in it with 4 pairs. So now let's bring the things together. Let's bring the cable together with the components. So now individual components turn into links. So when we mount this, we're getting transmission links, and there are different names for different links we have. So first of all, we have the part of the network which is fixed mounted. It is permanently mounted. You don't change it. You don't remove it anymore. It's called the permanent link. Permanent link is the link which is also measured when we are doing acceptance testing of a network installation. And this permanent link can be constructed in 2 ways. Details next week. Can be constructed in 2 ways. It can contain a consolidation point. So it's a sub-distributor, a passive one in a bigger room, or without, just a direct connection between the connector in the panel and the outlet in the wall. This is permanent link. If you add to the permanent link the patch cords you need to connect to the switch on the other side to the PC, is called the channel link. The channel link is the complete transmission line, but that's only when you do measurements on the channel link, you only do it in case of some trouble, some fault of an existing link. But it's not the measurement type of measurement you do for an acceptance test. Okay, let's stop it here. More details, closer to look to the different link models we'll do next week on the advanced training course. Okay, so performance level, as I told you, there is categories. We already used the words categories. There's also classes we used to have, and this is something which is often is mixed up, let's say. So what the difference between categories and classes? So categories, the word categories is used in conjunction with numbering, is used to define the performance level of components. Components is the plug, the jack, the cable, a patch cord. They are called components. If you combine now the components, the cables with 2 jacks on the ends, you get a link. And this link is usually tested in our area, Germany, Europe, tested against a performance class. Okay? The American standards are using the same expression category for the components and the cables and for the links. Okay, the numbering, as I said earlier, is oriented on the performance bandwidth level of the part or of the link. Okay, on the international standards, we also have the categories for the components. Okay, but when it comes to testing of a complete link, we switch to classes, and we combine the classes with letters, D, E, EA, F, FA, and some Roman letters for 1 and 2. Okay, so testing a link is always based on classes. Okay, and you have to make sure when you're doing testing to use an instrument which is properly accurate to do this measurement. Okay, but that's some detail we will discuss next week on the advanced courses. Okay, what performance level do I now need for certain applications? What bandwidth in megahertz do I need to run certain applications on megabits? So, and this is not linear, let's say. This is depending on the modulation system and the coding and so on. I compiled a little table to give an overview on applications and categories or classes of systems you need for certain applications. So let's just not talk too long about these details here. So just go to some important ones. So Ethernet, gigabit Ethernet, you see here, gigabit Ethernet What does it need? 1000 megabit Ethernet needs a bandwidth of 100 megahertz, not 1000 megahertz, but 100 megahertz. If you go up to 10 gigabit Ethernet, for behind here, the 10 gigabit Ethernet, 10,000 megabit of Ethernet is just happy to get a bandwidth of 500 megahertz. Okay, so if you know what application the customer wants to run on this, just go to the table and check for the bandwidth required for the certain application, the certain Ethernet speed you want to run on it. Okay, that's for the moment, that's all here with the table. Okay, now let's come to where we are sitting, where we as Softing IT Networks are sitting, to testing and measurement. What different test and measurement types do we have? We saw it already on the introduction where we grouped our instruments. So the very basic start of any testing of a link, of a copper link, is verification. So our expression here is verification. What is verification? Verification is just the basic test of the cabling. Check for the correct wiring. All later instruments or higher level instruments also start with a wire map test, because if a wire map is not properly done on a link, it does not make sense to do high frequency measurements on some crosstalk if the cable is not properly installed or properly laid out. Okay, so that's the very basic start, verification, just a basic test of the installation quality, let's say. But it does not give any indication what application can now be run over this system, because it had no relation to bandwidth and no relation to application. In the older days, when we started with measuring installations, the next level was automatically a big jump from a verification to a certification. Certification is the master class of the testing. It's using high frequency measurements and low frequency measurements, 14, 15 parameters, to get a complete analysis of the electrical performance of the link I was testing. And based on passing these electrical performance levels, we derive the application we can run on this. So if we pass a class EA test up to 500 megahertz, we know that 10 gigabit Ethernet should work properly on this system. So that's certification. Also, there's a jump in the cost of the measurement instrument. So if you buy a certifier, you're talking about the 10,000 euro class. If you buy a simple verifier, you're down maybe to 15 euros. Okay, and since there's a big gap between the very basic tester and the high-end tester, I think about 15 to 20 years ago, there was an invitation of a middle class of testing. It was so-called qualification. Qualification is also testing the wiring, of course, the wire map, but then it's doing a different test. It's using actually the application, the Ethernet protocol, to do testing. Because in the Ethernet parameters, where Ethernet is defined as a transmission protocol, it's also referenced how many faults are allowed in a transmission process to say that the transmission media is working or not. That's the basic behind it. So it's doing a kind of a bit error rate testing, as we see later on, to analyze the quality of the transmission line. And you can use this quality of the transmission line, this test, you can use as a documentation that this application will work on this installed basis. Okay. And the advantage is that the instrument is cost-wise somewhere in the middle between verification and certification. Okay. And there is also something new, active and troubleshooting. So a modern verifier and a modern qualifier does not stop at simply checking the transmission line. It's also can be used for active testing. So when the switch has already arrived and the network should go into operation, you can also use these test instrumentations to do the basic test of activating a network to see whether addressing is working, DHCP is working. Very important nowadays, is PoE working properly? Is the supply voltage for the remote, for the terminal unit, is it available properly? Very important test nowadays when you activate a network. So remember, high-end verifiers and qualifiers are also good for active testing and also, of course, troubleshooting on this. Here are a few samples of our instruments. Here, this is copper verifiers. So it starts with a very low instrument. Here, this is the new Cable Master 210. somebody we know for a while is the Cable Master 500, and in the top line you see the latest and greatest now we have is the Link Expert. Link Expert is basically also a very intelligent verifier. So people tend to love this instrument because it's about 60 euros, something like this. And it gives you a statement about is the wiring correct or not. So here you see the sample. This is the scheme, and this is how it's reported on this tester. Okay, you see 1 and 2 is some shortened, 7 and 8 is just open, is missing, it's always pairwise, and the other pairs in between are working fine. So that's a statement. That's a statement where you can start to search for faults. But the big problem you get now is you don't know where the fault is. So when you're lucky, you're opening one side of your link and you find the 2 faults in one link. Hey, great, lucky. If it comes to a worse situation, you see on the one side it's a short and the other side is the open. Not good. Okay, or if it comes to the really worst is that one of these problems is somewhere in the middle here. So these small testers in the very low range can't tell you where it is. If you want to know where it is, you have to move up the ladder to a high-end instrument. So like this one, like a Link Expert. The Link Expert is giving you far more information. It's also doing the wiring diagram and it's giving you already length information. How long is each pair of these cable? And if it comes to the worst, as you can see on the very opposite picture, is here is some problem on 2 wire pairs. So one wire pair is shortened, the other wire pair is open. And there's a TDR function built into this small tester, which gives you a clear indication where actually is the fault, the distance to the fault. And as I said earlier, it's also part of the functions only because you also have these active function testing. I just put in a few samples of the screens. It's DHCP test, do I get an address from the switch? PoE load test, does my PoE work properly? So you get all this information out of one small instrument, high-end verifier. Qualification. Qualification is what I said earlier, is testing with the application. So the major test of a qualifier is a kind of a BERT test, bit error rate test. It's sending for a while data and it's looping the data and it's counting, is the data coming back properly to me? That's actually one of the basic tests of a qualifier. But that's not the only test. In general, the more tests you do on a link, the more precise the result will be. And this is why, for example, this instrument here, the NetExpert, is combining the BERT test with a signal-to-noise ratio determination. The signal-to-noise ratio is also very important to see where is the problem coming from. Is it a noise floor, maybe, something like this? So if the noise floor is too high, it doesn't make sense to start with 10 gigabit application. So the combination out of this of noise floor checking or signal-to-noise checking and the bit error test is very, very good information for a pass-fail decision on that link. And also, there are other parameters which are important if you talk about gigabit Ethernet, is the delay time of the transmission of the 4 signal pairs or signals. It's send it over the pairs because the pairs have different lengths because of the different twists. The delay time to arrive at the other side of the link is different. And also it's important to see the difference between the slowest and the quickest signal part. And this is also part of the Ethernet standard to allow the maximal deviation of the individual signals here. And it's also part of the statement of the pass-fail statement a good qualifier is giving you. Also, again, the active testing, as we saw a bit earlier, active testing when we start up a network, we start up the active part. And of course, now it comes already to documentation. So a good qualifier can also give you some documentation on the qualification runs it did, which is a valid documentation of an installation, especially used in smaller applications or smaller installations. So that's a proper way to document an installation. So let's now jump to the certification. The classic acceptance test, as I call the master's class or the king's class of this. What we're now doing is we are using defined standards, cabling standards as a reference, as a source of limits of various parameters we are testing. And it's important to start with proper link definitions, as I mentioned earlier, permanent link and channel link and MPTL we get, and all these details we see next week. So these measurements, they're really doing action measurements, they're calibrated instruments doing measurements. These measurements are basing their pass-fail decisions on standardizations, on standards for copper networks. And as you can see here is a little glance into the world of standardization. As you can see, everything is standardized. The cable is standardized. The components are standardized. And if you build them together into a link, it's called a cabling. Although this cabling has its own specification, and this specification of the cabling is the one we are measuring in a certification process. And we get a pass if we have used proper cables, proper components, and the work was properly done. There are also standards out there to document how to do a proper installation. Of course, this instrumentation is also standardized how has the instrument to work and to what accuracy level this has to work. So that's a little glance into the world of standardization. All these limits from all the cabling standards on the world are already programmed into the instrument. So the trick for the installer is just to choose the proper cabling standard and to choose the proper topology, permanent link usually, and to start the measurement and save the data on the instrument. Okay, so when we do a little closer look into this now here, into this cabling standards, I have opened up the standards book a little bit for you. So you see that the standards performance levels are divided into these bandwidths with megahertz as we saw earlier. Okay, and we basically have two definitions on the world. The American ones, also called category, which we should not use here in international area or in European area. We have European standards, and the European standards are based on the international standard on the IEC 11801-1. Okay, that's the Bible of networking, let's say, the 11801. And there is the European standards derived, and from the European standards, we also derive local standards in every country of Europe, in every language of Europe. Okay, and what we teach our installers is to use the proper standard class E, class EA when setting up the instruments. So you have to be aware what you need. When you want to test up to 500 megahertz, you have to set the instrument up to test against class E. Okay, that's the way it is. What are we testing? There is a large number of tests an instrument can do. As I mentioned earlier, about 14, 15 measurements we can do. And we can group these measurements. We can group them roughly into low frequency parameters, high frequency parameters, and calculated parameters out of parameters we measured. And then we can also do another sorting in a matrix. Where is this parameter coming from? What the influencer of this parameter? So there's installation quality. So of course the wire map is down to installation quality. If the installer has done wrong wire mapping, it does not work simply. So the cable, what the cable is giving is some delay times and giving us the length indication. Connector has no length. The length indication is coming from the cable. And we have parameters which are typically based on the performance of the components, like this crosstalk stuff. Nowadays, modern data cables are so well designed and manufactured that most of the crosstalk problems are coming from the components, where we untwist it, where we have these 8 pins in the RJ45 connector. So that's more problem coming from the components. And we also have parameters, prominent parameters to test how good the cable and the connectors are matching. It's return loss, it's the number of reflections getting back, the quantity of reflections getting back from one link. So usually you want to transmit a signal, you start on the one side and want to have the same signal on the other side. The signal will get smaller because it's attenuated, it's gets smaller, but what you don't want is something that is reflected directly back, because all the reflections you get on your transmitter is missing on the other side. So if the cable is long, it might not end up with a valid signal anymore. Okay, all these parameters we learn next week. There are also now a certain group of optional parameters on the very outside, and there is only one parameter which sounds to me reasonable at the moment, and we have also included into the wire expert measurement, is this group of unbalanced DC resistance unbalanced measurements. But it has to do with PoE, with power Ethernet, and we will dig into these details next week just to give you an idea This is a parameter that's a new parameter on the tester, and this parameter is needed when we are talking about PoE. So when the tester is now properly set up and it's done a measurement, what do we get? So we're getting a few different result screens from the tester. So the tester actually we're using is our wire expert, of course. So you get the wire map screen, and what you also get is a summary screen, and you get tables for DC loop resistance, for example, and you get a table expressing the length values and expressing the delay and delay skew value on this. So these are called the low frequency measurements, the low frequency LF measurements. Okay, when the instrument is doing an RF measurement, a high frequency measurement, you get even more screens out of the tester, though. It starts again here with a summary screen when the test is finished. Lovely, we were happy and got a very nice green tick mark here. Then we can dig down into the details here. And then we see a complete listing of all the parameters which were tested. As I said, 14 to 15 parameters nowadays. If we go to the next and open up the next level of screen, we get a graphical interpretation of the next measurement. It's a measurement over frequency. Okay, this line is the limit line given by the standard, by the selected standard, and this is the measurement curves we get out of these measurements for 12 measurements we have to do next. And there's a cursor which indicates which was the worst margin on this. And we can even go dig deeper into this. We can isolate individual pairs and can have a look to the individual pairs. Okay, so we get a lot of information from the test. And actually, there's a very nice feature in the wire expert. It's called the locator function. If something would go wrong on this RF parameter, if one goes wrong, you would like to know where it goes wrong. Is it the beginning or the end of the link, or is it somewhere in between? And we have a system called locator, which is giving you a length interpretation of your link and where all the problems are coming from. Like here is something in the middle. Usually you got more crosstalk in the beginning where the jack plug combination is, and a little bit more next on the other side where the jack goes into the other plug. And here, somewhere in the middle, everything should be clear. But unfortunately, you got here an enormous spike. So somebody cut the cable in the middle and just matched it together somewhere. Okay, not a professional fixing of the cable. Okay, more about this also next week when we talk about all these high frequency parameters. What do we want? Finally, this is what we finally want. This is the protocol which you get out of a certification process, which is containing all these low frequency parameters, wire map, and all the high frequency parameters tested, including the graphs on this. Okay, that's the target where we want to go, and this is where we will end up next week on these protocols. These are different protocols we also can get out of a certification process. This is just a kind of summary protocol. Here we are using some different technology. Here we're using a coax testing. Also the wire expert can do coax testing. And interesting for tomorrow, also can do fiber testing. Fiber testing means insertion loss or attenuation testing plus length measurement, and also very important end phase inspection for a connector, for a fiber optic connector. Okay, that's it for the moment on the technical side. A few words to this little series of seminars. I've also included this slide here, giving you the dates when we do what here. So tomorrow is fiber optic, the basics, and I think the rest you can read from the slide as well. And feel free to join in again. And I think that's it from my side. I'm looking at Alex. I'm asking for some questions. So thank you very much from my side. And Alex.
Yeah, there was a lot of attendees. They say thank you very much for the nice presentation.
Oh,
to you, welcome. Alfred. No specific questions today.
Wow.
I think it was a wonderful presentation with a lot of details, no questions on it. And when was a question, I have answered it now.
Ah, okay, already answered. Okay, so very nice. And I think that's it for the day. And we will close it now.
We will close it now and see you tomorrow.
And see you tomorrow. And thank you very much for the compliments.
Thank you. Bye-bye.
Okay, bye-bye.